A-Level Pure Calculus, finding the volume of revolution. Sometimes we may wish to find the volume of a shape which has radial symmetry about an axis, such as an object that can be made on a lathe or on a potter's wheel. We can create a solid shape by rotating a section of a graph, say y equals function of x, around the x-axis. Now, to find the volume, we can divide the solid shape up into discs centered on the x-axis. We can let each disc have thickness delta x. So a disc at x on the x-axis will have a radius y, where y is equal to function of x. Now the volume of the disc will be pi r squared h, where r is the radius, and in this case is equal to y, and h is the thickness, which in this case is delta x. So the volume of the disc will be pi y squared delta x. Now we want to find the sum of all such discs, and the volume will be approximately equal to that sum. So the volume will be approximately equal to the sum of x going from a to b of pi y squared delta x. Now, the thinner we take delta x, the more accurate the result, so the volume is equal to the limit as delta x tends to naught of the sum x going from a to b of pi y squared delta x. Well, the limit is the integral. So we have the volume is equal to the integral from a to b of pi y squared dx. But we have to substitute y as function of x. So it's equal to the integral from a to b of pi times the function of x all squared dx. Let's have a look at an example. Show that the volume of a cone is given by the formula 1/3 pi r squared h. Well, to solve this, draw the graph of y equals kx. We can rotate the graph about the x-axis. The height of the cone is h. The radius of the base is r. So from the graph we can see the gradient of the line is r over h. In other words, k is equal to r over h. Now the volume is the integral from a to b of pi y squared dx. So in this case, it's the integral from 0 to h of pi times kx all squared dx. And we can take the pi and the k squared out to give the volume is pi k squared into the integral of x squared dx. Well, the integral of x squared dx is x cubed over 3, and if we put that between the values of 0 and h, that gives us pi k squared into h cubed over 3 minus 0. But k is equal to r over h, so that's pi r over h all squared times h cubed over 3, or pi r squared h cubed over 3h squared, which cancels to 1/3 pi r squared h, as was required. In example 2, the diagram shows a sketch of the region enclosed by the curve y equals the square root of x squared plus cos 2x, the x-axis, and the lines x equals 0 and x equals pi by 2. We're asked to find the volume of the solid formed when this region is rotated around the x-axis. The answer should be given in exact form. Well, to solve this, we can use the formula volume equals the integral of pi y squared dx between the limits a and b. So, this gives us that the volume is equal to the integral from 0 to pi by 2 of pi times the square root of x squared plus cosine of 2x all squared dx. Well, the square root and the square cancel, so we're left with the integral from 0 to pi by 2 of pi into x squared plus cosine of 2x dx. Well, when we integrate that, the integral of x squared is x cubed over 3, and the integral of cos 2x is equal to a half sine 2x. So we evaluate the expression by substituting x as pi by 2 and then subtract the value of the expression substituting x as 0. This gives us pi by 3 times pi by 2 cubed plus a half sine of 2 times pi by 2, or sine pi. And we subtract 0 plus a half sine 0. Now sine of pi and sine of 0 are both 0, so we're left with pi by 4 over 24 plus 0, take away 0 plus 0. And so we get the volume is equal to pi to the power of 4 all divided by 24. In example 3, if we rotate the blue shaded trapezium 360 degrees around the x-axis, we end up with a shape that's a part of a cone, called a frustum. So, by finding the volume of rotation around the x-axis of the blue shaded region in the graph, derive a formula for the volume of a frustum, that is, a section of a cone, with top radius a, base radius b, and height h. Well, to solve it, in the first diagram, let the equation of the graph be y equals kx plus a. Now, the graph goes through the point HB, so if we substitute x as h and y as b, we get b equals kh plus a, which can be rearranged as k is equal to b minus a over h. Now we know the volume of rotation is the integral of pi y squared dx between the two limits, in this case 0 and h. So we have the volume is equal to the integral between 0 and h of pi times kx plus a all squared dx. And if we expand the kx plus a all squared, we get the volume is equal to the integral of pi k squared x squared plus 2kxa plus a squared dx. Now, when we integrate k squared x squared, we get k squared x cubed over 3. When we integrate 2kxa, we get 2ka x squared over 2. And when we integrate a squared, we get a squared x. And we're taking that between the limits 0 and h. So we substitute h in place of x, and then we subtract, substituting 0 in place of x. And that gives us pi into k squared into h cubed over 3 plus 2ka h squared over 2 plus a squared h minus 0. But we know that k is equal to b minus a over h. So we've got the volume is equal to pi into b minus a over h all squared times h cubed over 3 plus 2 times b minus a over h times a times h squared over 2 plus a squared h minus 0. Now we can cancel some of the h's, and so this gives us pi into b minus a squared times h over 3 plus b minus a times ah plus a squared h. And we can take out the h over 3 as a common factor to give us 1/3 pi h into b minus a all squared plus 3 into b minus a times a plus 3a squared, which is equal to 1/3 pi h into b squared minus 2ab plus a squared plus 3ba minus 3a squared plus 3a squared, which all simplifies down to 1/3 pi h into b squared plus ab plus a squared. And that is the volume of a frustum. The volume is 1/3 pi h into a squared plus ab plus b squared. In example 4, we're told the graph shows the equation y equals x squared plus 1. The shaded area lies between the y-axis, the graph, and the lines y equals 2 and y equals 3. we want to find the volume of the solid formed by rotating the shaded area 360 degrees about the y-axis. Now up till now we've rotated always around the x-axis. In this case we're rotating the shape about the y-axis. So to solve this, we have the volume when rotating about the x-axis as the volume is equal to the integral of pi y squared dx between the limits x equals a and x equals b. But when rotating around the y-axis, this will become the volume is equal to pi x squared dy between the limits y is equal to a and y is equal to b. Now, we were originally given the equation y equals x squared plus 1. That can be rearranged to give x squared is equal to y minus 1. And the required volume is equal to the integral of pi x squared dy. So the volume is equal to the integral of pi times y minus 1 dy between the limits y is equal to 2 and y is equal to 3. Now when we integrate y, we get y squared over 2. And when we integrate minus 1, we get minus y. So we want to substitute 3 into pi into y squared over 2 minus y, and subtract substituting 2 into pi times y squared over 2 minus y. And this gives us pi into 3 squared over 2 minus 3 minus pi into 2 squared over 2 minus 2, which is equal to pi times 4.5 minus 3 minus pi into 2 minus 2. And that works out to be 1.5 pi. So our volume is 1.5 pi.